talk about chapter 7 of the lecture notes. I have sent the chapter 7 and all the lecture notes to you before. Okay, and I noticed some typos when I was preparing for the lecture yesterday. I will update the typos in the lecture notes and send you a new one. So what we're going to do is actually to study quantum mechanics in crystalline structures. I think this is a very important chapter because it will help you understand lots of current technologies that you encounter in electrical engineering, like compound semiconductors and so on. So, if you define a crystal, you think of a periodic lattice. Okay, in 2 dimensions, we can draw them very easily. If something happens periodically in 2 dimensions, it might look something like this. And these are the nucleus of the atom. They're usually bound and stationary, and we assume that they are not moving. Of course, they vibrate, but we don't assume that they're vibrating. And to make things simpler, we assume that they do not move. Okay, this is in 2 dimensions. And in 3 dimensions, then it's harder to draw. You might have crystalline structures that look like that. This is a simple cubic lattice. Okay? And you have other kinds of crystalline structures as well. This is 2D, this is 3D. And of course, we can study the 1D problem first. To make life simpler, we just look at the 1D periodic lattice and ask ourselves, what happens to Schrödinger equation when we have just a 1D periodic lattice? So if we have a 1D periodic lattice, it might be just expedient to study the simple potential one problem. Okay, a simple periodic potential problem, and ask ourselves, what kind of theorems can be derived by just studying this simple 1D problem? Okay, I have a picture of it. I think this might be the x-axis, and then this is just the sketch of the potential that we have in the 1D lattice. Okay, so we're going to study how an electron behaves in this simple lattice. But in actual fact, the behavior of electrons is quite complicated. If we have a semiconductor material, for instance, we do not just have one electron flowing in the lattice. Like if this is the lattice in 2 dimensions, we have many electrons. So we have many electrons moving around. And they might move around, and then there will be, of course, the nucleus that are positively charged, and the electron will move about. The electrons will move about, and they will also see each other. There's not just one single electron in the lattice. There are actually billions and billions of them moving around in the lattice. Okay, so just not one electron. But to make life simpler, we assume that all the other electrons give us an effective potential. Okay? So is one electron moving in presence of many other electrons. But this is an extremely complicated problem to solve. If you want to solve many electrons interacting with each other, that's usually called an n-body problem in physics, and it's extremely difficult to solve. So we want to simplify things. And we say that if we have an electron, the other electrons just form an effective potential. Okay, the other electrons form an effective potential. So this electron is moving in the presence of the other electrons, which form an effective potential. We will also assume that the effective potential formed by the cloud of the other electrons is periodic, because these electrons are smeared out all over the structure, their nucleus around, and effectively the potential in the background is also periodic. So we study the problem of one electron moving in a periodic potential background, which not necessarily just come from the nucleus of the atoms, but this effective potential also comes from the other electrons that are moving about uniformly in the background. Okay, we study this rather simple problem. There's one thing. Another thing that you should take note of is that these are nucleus. So when the electron moves about, they collide with the nucleus. The nucleus are not truly stationary. They vibrate. Okay, they could vibrate. And when they vibrate, they give rise to vibrational modes called the phonons. Okay, you will learn what a phonon is later on. And we will not study, we will ignore electron-phonon coupling. Okay, in this picture, we just ignore those coupling, because those coupling is quite difficult to study. So we study the simple problem of just an electron moving in a periodic potential. And this, in a sense, is like what you studied before. You studied the case of a tight binding model. You studied how an electron would behave in the one simple one. And then you use the tight binding model and argue that when you have two wells next to each other, then the electron would hop between these two wells, and then there will be split energy level, and then if you have three of them, you have more energy levels and so on. Okay? So let's do this very simple problem. This is the tight binding model, TBM. This is the periodic potential model. This is usually called or studied by what is known as the block-locate theorem. Okay. So if you were to write down the Schrödinger equation in general, we will have the fact that the Schrödinger equation will satisfy this rather simple looking equation. This rather simple looking equation. And then there will be a background potential that this electron sees, and we call it VP X to be agreeing with the lecture notes that we have. And then there will be this wave function that this equation has, and this wave function is an eigenmode. Okay, and we write that the eigenmode should be something of this form: e to the I k x u p of x, which means that because of the periodicity, the wave that propagates through the structure, if there's a wave, the wave that propagates through the structure has to be something of this form. So you imagine a wave going through this structure, and that wave has to be something of this form. It is a plane wave modulated by a function upx. And then you argue that if this is in fact a solution, if I were to translate my thing by x plus NA, where A is the period of this periodic potential, A is in the spacing or the period of this periodic potential, then this solution would evolve to be something like this: UPX plus NA. And if I were to do that, then I can always say that I can let x prime be equal to x plus NA, okay, or x is equal to x prime minus NA. Then you can see that the x is actually the x prime, and if I do a change of coordinate system of this equation, then I will have h squared over 2m. Or I can actually do the reverse. I can actually make things simpler. Or let me just do it this way anyhow. We square the x prime square plus bp x minus na, x prime minus na. Okay, then I will have k of x prime minus na, but this gives me the same thing. Okay, e of psi k x prime minus na. Okay, if I were to look at this equation, this becomes itself. By definition, this is a periodic potential. This becomes itself again. So what I should have in the next line is that the equation I have is something of this form. B prime x prime, because this is itself again, and that this thing, if I were to substitute this in, okay, if I put minus na instead of here, I would get something like e to the I. If I let x prime be x prime minus na, this would be just k x prime e to the minus I na up x prime minus na, and then is equal to e to the I k x prime e to the minus I na up x prime minus na. Okay, you can see that I can cancel this constant out. Okay, and since the two equations should have the same solution before translation and after translation, I must have the fact that this thing must be just up of x prime. Okay, I conclude the fact that in order for this to be a solution to Schrödinger wave equation with a periodic potential, that upx must be periodic plus na, x prime plus na. Okay, no, I shouldn't say that. That if I translate this by something, it should be itself again. Okay, I should have this fact that this function here has to be periodic. Okay, this function here has to be periodic. And that is essentially the essence of the Bloch-Fouquet theorem. The Bloch-Fouquet theorem says that if I have a wave going through a periodic lattice, the waveform must be something of this form, a plane wave modulated by a function, and this function has to have the property that it is periodic. Okay, that is the Bloch-Fouquet theorem in 1D. Okay, are there any questions regarding what the Bloch-Fouquet theorem is? And if you imagine this, the periodic lattice usually has very small dimension at the atomic level. So UP might be functions that looks periodic on the length scale of A. Okay, it's periodic on the length scale of A. Whereas the background wave, e to the ikx, if I were to draw e to the ikx in the background, it might have a much longer wavelength. Okay, it could have a much longer wavelength. So you can imagine that there's a plane wave propagating through the structure modulated by this periodic function. The periodic function varies a lot more rapidly compared to the plane wave in the background. So are there any questions regarding this Bloch-Fouquet theorem? So if that is the case, then we can argue that since this is a periodic function, it must be expandable in terms of a Fourier series. I can expand it in terms of, say, 2I n pi x over a kind of thing. So when x is equal to a, it just repeats itself. Okay, so I can use this kind of Fourier series expansion to expand this periodic function, and this can be generalized to higher dimension. But let's look at Schrodinger equation more closely. If UP is something of this form, and let's plug this form into Schrodinger equation and see what we get out of it. Okay, let's plug this into Schrodinger equation and see what we can get out of it. So if we look at this, it's mainly this term that is important. We use the fact that the square, the x squared, say the product of two functions, ux, dx. If we use the rule, this would be u double prime x dx plus 2 u prime x v prime x plus v ux v double prime x. If we remember this chain rule, what is that?
The chain.
Yeah, the chain rule. Okay, if we use this to plot this and then figure out what this should be, okay, then we find that this would be something like, if I differentiate the first term twice, I get minus k squared e to the I kx utx. That's the first term. And then if you look at the second term, I would have something like plus 2I k e to the I kx ut prime x, okay, plus the third term, which would be e to the I kx ut double prime x. So that term will just become this over here. And if I write down the wave equation, the Schrodinger wave equation in full now, with the minus h squared over 2m properly, then I should have this equation, k squared upx plus 2i k ut prime x plus up double prime x plus vpx upx is equal to e of upx. Okay, so the periodic function must satisfy this equation that I have derived over here. Okay, you just substitute that into that equation, you cancel e to the ikx from both the left hand side and the right hand side. You're left with that equation for the periodic function. You can see that in the long wavelength limit, that is, if k tends to be 0, if k tends to 0, okay, which we call the long wavelength limit, if this is the case, then we can drop terms like this and like that, and then we are back to something that looks like Schrodinger equation again. Up double prime x plus bx upx must be equal to e upx. Okay? So if the electron is moving through the lattice with a very long wavelength, then UP essentially satisfies Schrodinger equation. And sometimes you only keep this term. Okay, in the long wavelength limit, you make a correction to this term by keeping only this term. And this is essentially like 2ik ddx of up x. And ddx is like a momentum. Okay, this is like a momentum p in the x direction. So if you keep only this term, this is in the literature known as the k dot p approximation. It is not only done here, but it can also be done later on in the effective mass approximation. Okay, and of course you can keep this term to its root glory and keep the k squared term as well. How do we solve this problem? This problem can be solved by converting this into a matrix equation, for instance. We can convert this into a matrix equation by using the subspace projection method. We expand up in terms of a basis function, a set of basis functions, and then convert this into a matrix equation. So one way to solve this problem is, for instance, let up x be written as the sum of basis functions, like an sine n of x. Okay. Say this is a 1D periodic function. It will be a function that repeats itself. It will become itself again at the point A, 0 to A becomes itself, and then it repeats itself again. Okay. So we can actually use a finite element method or subspace projection method and break this into tiny pieces. Is one way to solve this problem. Okay, and then the first unknown and the last unknown must be the same due to the periodic condition, because this is the periodic function. So up of 0, okay, and if we call this delta x, and we call this m delta x, if we break this into endpoints, the periodic boundary condition must make this to be true. Okay, this is the periodic BC. Okay, and then you can start giving unknowns to, you can give the first one, second one, but not the last one, since they have the same unknown as the first one. You can give each of this a triangular function, and then convert this this equation into a matrix equation by the subspace projection method, and then you can solve that matrix equation. Another way is that you can expand this in terms of a Fourier series. You can also use this maybe using a finite basis n to the minus n to n, a n e to the 2I n pi x over a. This automatically satisfies the periodic boundary condition. Substitute that in, do the testing, and convert that into a matrix system. Okay? And the question to ask, is the matrix system that we obtain finally Hermitian? Is the matrix system Hermitian? Okay? Then we ask ourselves, what is the definition of a Hermitian operator? Is this operator d squared dx squared, okay, u double prime x is equal to d squared dx squared ux. Is this a Hermitian operator? How do we test to see if it's a Hermitian operator? Okay, we go back to the definition of what a Hermitian operator is that if we find a matrix representation of a Hermitian operator, that matrix representation must itself be Hermitian. Okay, so we can try this with a maybe fm x d squared dx squared, and then we can do something like this if we use direct notation fnx, and this is the, say, matrix element a n m would be this thing over here, And by definition, this in one dimension is given by this. And if we think of this as something that satisfies the periodic boundary condition, okay, the first one and the last one must be the same, but we can think of these functions as subdomain basis functions that only consist of a finite support, okay, that is zero outside the domain, but non-zero outside the domain. And if we were to do integration by parts on this, say if we integrate this over the support of the function, okay, then if you do integration by parts on this, then we get d dx fn star of x d dx fm of x. And then with a minus sign out front. And then there should be another term that accounts for the fact that we have integrated it once. We should be f sub m of x, and then a and b. Okay? And this term can be made to vanish in a number of ways. If the basis functions are subdomain basis functions, then when you integrate from a to b or over an interval for which this is 0, then that can be made to vanish. And if I pick this integration interval to be from 0 to a to be more general for the periodic function, and then this should be from 0 to a. Okay, this can be made to vanish by a number of means. One is to pick subdomain basis functions so that these functions are 0 outside that subdomain. Another one is to impose the periodic boundary condition. The first value and the last value should always be the same. This first value and the last value should always be the same. And then you can also make that term vanish if you were to impose the periodic boundary condition. So usually we just end up with this. So this is the matrix element A and M. Does this represent a Hermitian matrix? If it represents a Hermitian matrix, it should be equal to A, M, and complex conjugate. Okay. So if you look at, if this is defined to be A and M, A and M will be defined with these two transpose. If we take the Hermitian, the conjugate again, and get back inside. So you can see that this represents a Hermitian operator because its matrix representation is always Hermitian. Okay? So that is one thing that we know. But what about this operator? There's another operator that is in place over here, which is I d dx of upx. Is this a Hermitian operator? No, right? What do you say is no?
Just following the same procedure as we take the complex, but there's an I in front. So
Okay. Actually, it turns out to be actually Hermitian. It's kind of counterintuitive, but that is a Hermitian operator. Remember that a momentum operator p hat is just minus I, is h bar k hat, right? P is h bar k, so p hat is h bar d dx with a minus I in front. Okay? We previously proved that p hat is an observable. Because p hat is an observable, its matrix representation must be Hermitian. Okay, its eigenvalue must also be real. Okay, I can prove this to you that it's Hermitian again quite readily. Let's go through that. If an operator is Hermitian, its matrix representation is always Hermitian. Let's remember this to be the point. So if I take this and I try to find, say, fm I d dx of fn Okay, if I try to find this quantity, then this quantity by definition will be, let me do 0 to I again, and star x, I dx, and x. Okay? And then if I do integration by part, I will make this into minus 0 to a dx ddx and star of x with an I somewhere out front that I can take out, and then fn of x. Okay, if I do integration by parts. And then of course there is a leftover term that comes from fn star x I fn x. This is the leftover term. I can always make this term by using the periodic boundary condition. Okay, I can always make it vanish. The first point and the last point are always equal to each other. And so I always make that vanish. And then I'm left with this. This is the matrix element, say, Bmn is equal to this. Okay? And if you look at this, this is just the complex conjugation of Bmn, right? Okay? That is always true. So Bmn is always a complex conjugation of Bnm. So this must be a Hermitian operator. It has to be a Hermitian operator, as we said before. This is very similar to the momentum operator. Momentum operator is Hermitian because it represents an observable that we can actually observe in the real world. Okay, so if you look at all these three terms, they are form of Hermitian operators. And if you go about doing the subspace projection method, you go to the normal procedure of finding the matrix representation of the whole operator. Then you end up with a matrix system that will look something like that. H. Okay, I don't know if you want me to go to the detail. Maybe I can go through the detail a little bit with you. Let me just write it down. Okay, that this operator is apparently a function of k. Okay, if I take out this as an operator in total, I will find a matrix representation of this entire operator. Okay, it will give me this matrix system by the subspace projection method. And then I will have this eigenvalue, okay, times the right hand side, B dot A. We have figured out how to use a subspace projection method to convert a differential equation into the matrix equation. And then an element of this matrix, okay, is just the matrix representation of this operator. And if I call this operator in total, okay, that operator in total to be H bar UPX. Okay, if I call the entire left-hand side of this equation to be H hat UPX, okay, that operator will represent this first term plus this last term. Okay, I can write it down for you later on. And then B and N is just Pm, Pn. Depending on whether you use orthogonal basis or non-orthogonal basis, this is usually called a gram matrix. Okay, this is usually a gram matrix. And then the H hat, I can write it down explicitly for you. H hat is actually H squared over 2m minus k squared plus 2ik d dx plus d squared dx squared. This is my H hat plus a bpx. Okay, this is my H hat. So if I think of this as an equation that is something like this, if I think of this as an equation that looks something like this, and if I go to the subspace projection method using this expansion, convert this operator into a matrix system, the matrix system will be given by this. And all the elements of the matrix system should be Hermitian, because I proved to you that this term is Hermitian. In other words, this term is Hermitian, this term is Hermitian, the rest are all Hermitian. So I have a Hermitian system. This is Hermitian. This is a grand matrix. Okay, by the definition of this grand matrix is Hermitian. So what do you know about the eigenvalue E? The eigenvalue E must be real, right? Some of the knowledge that you should remember from your matrix theory. E has to be a real number. Okay, since this is Hermitian, this is Hermitian. E has to be real. The most general case is that A dot X is equal to lambda X. This is, if A is Hermitian, implies that lambda is real. Okay, but this case can be proved when also this is a EV problem, eigenvalue problem. This is called a generalized EV problem. Okay? When you have this B on the right hand side, not being an identity, this is called generalized eigenvalue problem. You can easily prove that if B is Hermitian, H is Hermitian, E has to be real. Okay, I won't go through the proof. Very similar to the proof that we did for the Hermitian case. So E has to be real. And E must be a function of K because H hat is a function of K. Okay? So E must be a function of K. So what you have after solving this problem is that you have the case of a Venn diagram for this locate mode, locate theorem. This